Welcome to your Finite Math Lesson 2.1 on solving systems of equations. So, the objective today is that you will solve linear systems. A system of linear equations is just two or more equations with at least two variables that can be written in the form ax plus by equals c and dx plus ey equals f. A solution of a 2x2 system like this, meaning two variables and two equations, is an ordered pair x, y that satisfies both equations. If there is no point of intersection, if you were to graph the two lines, then there is no solution. In this case, the lines are parallel. And if one line graphs on top of the other line, then there are infinitely many solutions. We say that the lines coincide, and every single point on that line is a solution to both equations. And so, since there's an infinite number of points on a line, there's an infinite number of solutions. So here's what it looks like. If we are to graph to solve, if the two lines intersect, you've got a single solution. If one line graphs just right on top of the other, you have infinitely many solutions. And if there are two parallel lines, there are no solutions. All right, so we're going to graph the linear system and estimate the solution. Then if you want, you can check it algebraically. We've got 4x plus y equals 8. 2x minus 3y equals 18. Now I suggest putting it in slope-intercept form to be able to graph. If you need to review graphing, you need to go back to the Chapter 1 videos and review graphing the lines. You just graph both lines on the same coordinate system, and then you see where they intersect. And so they intersect at the point 3, -4, and that's your solution. And then you can check it algebraically by plugging in the x value for x and the y value for y. So you plug in 3 for x and -4 for y, and you get 12 minus 4, and that does equal 8. So it works in equation 1. We need to double check equation 2, so we do the same process. 2x minus 3y equals 18, so 2 times 3 minus 3 times -4. So 6 minus -12 is 6 plus 12, which is 18. So our solution is 3, -4. Now, graphing to solve is nice because you see physically what's going on and why the why the two values, the x and y value, are the solution. But honestly, I prefer other methods for solving systems of equations because especially if the numbers aren't whole numbers, it's really hard to tell what the solution is from the graph. So we're going to cover two different algebraic methods, substitution and elimination. First one, we'll look at a substitution, and it's really nice if you have one variable that has a coefficient of 1. Otherwise, it gets a little messy, but if you have a variable with a coefficient of 1, using substitution is a great way to go. So what you want to do is you want to identify an easy variable to solve for. In other words, the one that has a coefficient of 1, or even -1 would be easy. So we've got an x here that has a coefficient of 1 in equation 2, so we're going to solve equation 2 for x. So we're going to be subtracting that 3y over, and we'll get x equals -3y plus 3. So what this means is we have something that equals x exactly. And what we can do is we can take this expression and plug it in for x in the first equation, and that takes care of a problem for us. The whole reason we can't solve for something with just one of these variables, one of these equations, is because we have two variables. So if I replace x with -3y plus 3 in this first equation, I now have an equation that's in terms of just one variable. So let's do that. So we're going to substitute for x in the first equation and then solve for y. So I've replaced x with -3y plus 3, or I have substituted -3y plus 3 for x. So now I want to simplify and solve, so I need to distribute the 2, and that's going to give me -6y plus 6, and then plus 5y equals -5. So that would give me -6 plus 5y is -y, plus 6. I would subtract the 6 over, I'd get -y equals -11, and then divide by -1 to get y equals 11. All right, so now I'm going to substitute the value of y into any of the originals. It's really easiest. You'll be able to solve straight away if you plug it into the x equals -3y plus 3 equation, because it'll be really simple just to simplify and solve there. So we'll have -3 times 11 plus 3, so we have -3 plus 3 to negative 3 plus 30. Negative 33 plus 3, which is negative 30. So your solution is negative 30, 11. And again, you can check your solution by plugging into both equations, and we get true statements there. So you just plug the x value in for x, the y value in for y in each equation, and make sure that you get true statements. All right, now we're going to use the elimination method, and usually this is my preferred method. The main thing you want to make sure is that your x's are lined up, your y's are lined up, and then you have your equals, and then you have your constants. Okay, and so we do. We've got 3x minus 7y equals 10, 6x minus 8y equals 8. All right, so step 1, we want to get opposite coefficients in front of one of our variables so that when we add the two equations together, one of the variables is eliminated. So I'm going to multiply this first equation by negative 2 so I can get rid of my x's. And the reason that'll work is negative 2 times 3 will be negative 6. And so that'll give me opposites for my x's. And so when I add the two equations together, the x's will cancel out. Now, even though it's the x's I'm interested in, if I'm going to multiply anything in this top equation by negative 2, I have to multiply everything in the top equation by negative 2. So I'm going to get negative 6x plus 14y equals negative 20. And then I'm going to recopy my second equation, 6x minus 8y equals 8. I'm going to add the two together. And when I do, let's go back and look at it. Negative 6x plus 6x zeroes out. 14y minus 8y is 6y. Negative 20 plus 8 is negative 12. So we get 6y equals negative 12. Well, we can solve that for y. We'll divide by 6 and we get y equals negative 2. So now I can take y equals negative 2 and plug it back into one of the original equations and solve for x. Let's use equation 1. It really doesn't matter which one we use. So let's use 1. So I'm going to substitute negative 2 for y. So I'm going to have 3x minus 7 times negative 2 equals 10. So that's going to be 3x plus 14 equals 10. So I'm going to subtract 14 from both sides. And that's going to give me 3x equals negative 4. Divide by 3, I get x equals negative 4/3. So the solution is negative 4/3, 2. Now here's a case where that would have been very hard to see that that was the exact solution from the graph, because it's very hard to tell negative 4/3 from, negative 1.3. Negative 4/3 is negative 1.33333333. So, that would be very hard to distinguish. And even if your graph is small enough, even negative 1.5, that would just be hard to tell what x is exactly. Okay, now we've done 2 by 2s, and that should be very familiar to you. Remember last year in Algebra 2, and also if you took pre-cal last year, you probably went over these also, the 3 by 3 systems. Okay, so 3 by 3 systems have 3 equations and 3 variables. And we're going to use a combination of elimination, substitution most of the time to solve them. This one, we're pretty much going to be using elimination throughout. The reason this is challenging is because there are 3 equations and 3 variables. So what we want to do is we want to make it 1 degree easier by getting down to a system of 2 variables and 2 equations. So somehow we want to combine 2 of these equations to get rid of a variable, and then we want to combine any other 2 equations, either any other combination of 2 equations to get rid of the same variable, and we'll have a 2 by 2 system. Well, we can work with those, we just did. So that's our method here. So we're going to rewrite the system as a linear system in 2 variables. So let's see, we're going to add 2 times equation 3 to equation 1, and what that's going to allow us to do is get rid of the y's. So we're trying to get in terms of x and z. Y is a good choice of the elimination variable because you've got this equation 3, that has just a negative y there. It's very easy then to transform this equation to opposites of the other equations as far as y is concerned. So I did 2 times equation 3, that's down here. And here's plain old equation 1. So 2 times equation 3 is going to be 6 times 2 is 12x minus 2 times y plus 2 times 4z, so 8z, equals negative 1 times 2, so negative 2. So let's add these together. And so we're going to get 16x, the y's cancel out, plus 11y equals negative 1. So that's your new equation 1. To indicate that it's a new equation 1, I usually put a 1 star there, and I put that in a little circle. So I've labeled it as equation 1, and I know it's the new one because it's got the star. So now I want to combine either equation 1 with equation 2 or equation 2 with equation 3. Okay, and I want to get rid of y again, because the idea is to end up with a system in terms of x and z in this case. So if I multiply equation 3 times negative 3, that's going to give me opposites of what I had in equation 2. So when I do that, here's equation 2, 2x minus 3y plus 5z equals negative 14, and I just got that from equation 2. And now I'm going to multiply equation 3 times negative 3. So that's going to give me negative 18x plus 3y minus 12z equals 3. So I'm going to add, so that's going to give me negative 16x, the y's cancel out. 5z minus 12z is negative 7z equals negative 11, and that's my new equation 2, or like I like to call it 2 star. So I would label that 2 star with a little circle around it. Okay, the reason I do that is it helps me keep track of my 2 new equations, plus whenever I'm getting ready, okay, am I ready to solve a 2x2 system? Do I have my 2 star equations? I do. I know to work with those 2 equations. Alright, so here's my 2 new equations. I need to look to see if I need to multiply anything. I've got 16x plus 11z equals negative 1, negative 16x minus 7z equals negative 11. Well, fortunately, I've got opposite coefficients for my x's, so I can solve for z just by adding the 2 equations together. So 11z minus 4z is, minus 7z is 4z. And that equals negative 1 minus 11, that's negative 12. So z equals negative 3. So now the question is, well, what do we plug this into? Well, you don't want to go back to the very original, because then you'll have 2 unknowns. You still don't know x and y. What you want to do is you want to go back to one of the new equations, one of your start equations, and plug z in there. And when you do that, you're going to get x equals positive 2. Okay, so if I plug this in, let's look. If I plugged it in here, I would get 16x plus 11 times negative 3, so that's negative 33. I add it to this side, I get 16x equals 32, divide by 16, and that gives me my x equals 2. Now I know 2 out of the 3 variables, I know their values, so I can go back to one of the original equations, why not equation 3, and solve for y. So I'm going to plug in 2 for x and negative 3 for z. And so that's going to give me 12 minus y plus negative 12 equals negative 1. So negative y equals negative 1. Divide by negative 1, you get y equals 1. So your final answer is going to be 1 to negative 3. All right, let's look at example 5. To raise money for new football uniforms, your school sells silk screened t-shirts. Short sleeve t-shirts cost the school $5 each and are sold for $8 each. Long sleeve t-shirts cost the school $7 each and are sold for $12 each. The school spends a total of $2,500 on t-shirts and sells all of them for $4,200. How many of the short sleeve How many of the short sleeve t-shirts are sold? Okay, so we're going to write verbal models here. One is for the cost, okay, and then the next is going to be for revenue. We've got short sleeve cost, 5, times short sleeve shirts, so x, plus long sleeve cost, so 7, times long sleeve shirts, so y, equals the total cost, which was $2,500. Okay, so we're going to look at revenue now. So that they make $8 or bring in $8 on each of the X shirts, the short sleeve shirts, plus they bring in $12 for each of the Y shirts, the long sleeve shirts, and that's going to equal $4,200. So now you've got your 2 equations, 2 variables. Well, we can do that. So we need opposites in front of one of the variables. So let's see. 5 and 8 don't have any common factors to them. So what we can do is we can just multiply the top by negative 8 and multiply the bottom by 5. Okay, you just look at what the other equation has and make one of them negative, and then we'll end up with opposites. So we're going to take 5x plus 7y equals 2500 and multiply by negative 8, and so we'll get negative 40x minus 56y equals negative 20,000. And then we're going to multiply 8x plus 12y equals 4200 by 5. And we're going to end up with 40x plus 60y equals 21,000. And then we're going to add the two equations together. The x's cancel, and we end up with 4y equals 1,000. So we divide by 4, and we get 250. Okay, that's the number of long sleeve t-shirts. We want to know the number of short sleeve t-shirts. So to do that, we're going to plug the 250 into one of the equations. Might as well use equation 1. And so we're going to get 5x plus 7 times 250 equals 2,500. And so that gives us 5x plus 1,750 equals 2,500. So we subtract the 1,750 and then divide by 5, and we get x equals 150. So 150 short sleeve shirts. And so the correct answer is C. Okay guys, thank you so much for taking good notes and paying such good attention to the video. If you don't understand any part of it, feel free to go back and watch it again. Try the problems to try on your own. Have them attempted when you come to class to get full credit for your notes. Okay guys, have a great day. I will see you soon.